Hello dear students, welcome back to the lecture series on theory of semigroups. Today in this lecture we will discuss the existence of tensor product in acts over monoids. So let's first define we take first some basic notions here. Let suppose we have two bisystems, say A and B. Let A be a bisystem which is left T and right S. It belongs to T and right S. So this A is a TS bisystem. It belongs to TENS S. That's a notation. And B is also a bisystem. It is in S. It's a left S. It belongs to S, E, and S. Then we have U here. U. And we have one more bisystem, that is C. C belongs to T, ENS, U. So they are all bisystems. A is TS bisystem, B is SU bisystem, and C is TU bisystem. Okay. Now we know that this A cross B is also a bisystem. Then A cross B is also a bisystem. Then we know that this we can define the order on we can define the action on A cross B. Then A cross B is an sorry it is a TU. It's a TU bisystem. It's a TU bisystem. That is this A cross B. It belongs to T, E, N, S, U, where the action is defined by where action is defined by. So we need to show that it is TU. So the action of T should be from left and the action of U should be from right. So it's T times AB is equal to TAB, and AB times U is equal to ABU for all AB belongs to A cross B, and this T belongs to T, U belongs to U. So this is the action here, and with respect to this action, A cross B is a TU bisystem. A cross B is a TU bisystem. Now we define a relation. Next we define a relation T on A cross B by. Let's define the relation on this cross product A cross B by T is equal to the following pairs A as B, A as B, such that this A, B, it is in A cross B. That means A is in A, B is in B, and this S is in S. And let tau be a congruence generated by this relation T. It's an equivalence, actually, not congruence. Let tau be the equivalence. Tau be the equivalence generated by T, generated by this relation T. Okay, we denote this the A cross B over tau by, let's take the following notation. Let's denote this A cross, let define, which we define this A, this notation over S equal to A cross B over tau. Okay, and the tau class of any pair A, B of tau class will be denoted by A tensor B. That means A tensor B belongs to actually this set A tensor B over S. It's equal to A cross B over tau. So this is called a tensor. This notation is called the tensor. So A tensor B over S is actually A cross B over tau. It's a set of equivalence classes, and each equivalence class of any pair will be denoted by A tensor B. And our aim is to show that this A tensor B over S with a relation tau natural is a tensor product, is a tensor product of A and B over S. So we try to show that this. And one thing is trivial, that since this pair ASB and ASB, this pair, it belongs to T, and T is subset of tau. So that means they are tau related. So which means that their tau classes are equal. That is A tensor AS tensor B is equal to A tensor SB. This is true for all A belongs to A. For all A belongs to A, B belongs to B, and S belongs to S. This holds. Because they are tau related, therefore their tau classes are equal, but the tau class of AS comma B will be denoted by AS tensor B, and tau class of A SB is denoted by A tensor SB. So they are equal actually. To prove to verify that this A tensor B over tau, A tensor B over S with this map tau natural is a tensor product of A and B over S, we first prove the following lemma. So what's that lemma? Statement of the lemma. Two elements A tensor B and C tensor D in A tensor B over S are equal if and only if either they are equal as pairs, or we have following set of equations, or there exist the following elements A1 up to an minus 1 in A, then b1 up to bn minus 1 in b, in b. So these elements are in B, they are n minus 1 elements in B, and we have these two n elements S1 up to Sn, then T1 up to Tn, they are in S, they are in S, such that we have the following set of equations, such that we have following set of equations. Such that I will write those set of equations in the next page. So we have the following set of equations: A equal to A1 S1, S1B equal to T1 B1. Then we have A1 T1 is equal to A2 S2. Then this S2 will move here, S2 B1, it should be B1 here, S2 B1 is equal to S3 B2. Then we have this A2 will come here, and I have here this, not here S3, sorry, this is actually T2, it's T2 here. Then T2 will come here, A2 T2 is equal to A3 S3, then S3 will come here, and then B2 will come here, S3 B3 is equal to T3 B3. And what will be the general step? The general step is like this: AI Ti is equal to AI plus 1 Si plus 1, and then we have here Si plus 1 Bi, this is equal to Ti plus 1 Bi plus 1. So this I is varying from now, because here I is now 3, so its I varies from 3 to n minus 1, 3 to n minus 2, sorry, 3 to n minus 2. And at the nth stage, what we have, an minus 1 tn minus 1 will be equal to an minus 1 tn minus 1, that will be equal to an, not, we don't have an actually, so it will be the last element, that's C, actually it will be C here, CSN, should be CSN, okay, it's CSN, and this SN, then we have here SNB n minus 1, that will be equal to TN, and finally D, not T and D, it's just D, not T and D. Okay, so these T's are not n minus 1. Let me see the previous page, they are just T minus 1, okay, S1 S2 Sn, then T1 T2 up to Tn minus 1. Okay, so these are the set of they must satisfied if A tensor B is equal to B tensor C tensor T. So so this is a statement of the lemma: two elements A tensor B and C tensor D are equal in A tensor B if and only if we have these set of equations which starts from A and B and ends with C and D, like this. Starts from A and B and ends with C and D. So name it, say star these set of equations, suppose. Let me name these as star. Proof of the lemma. Assume star holds. We show that A tensor B is equal to C tensor D. We have A tensor B is equal to, what's A from this equation is what's A is equal to A1 S1. So let's insert the value of A here. So it's equal to A1 S1 tensor B, and the same as A1 tensor S1B as already explained. Now this equation A is equal to A1 S1, it is by star. Okay, I applied this equation star here, and this is equal to A1 tensor, and this one S1B, it's equal to T1 B1. It's equal to T, by T1 is in S, it's again by equation star. Okay, next this A1 star T1B is same as A1 T1 star B, as already explained it. It's equal to A1 T1 star B1, but this A1 T1, it's equal to A2 S2 star B1, again by equation star, and that's equal to A2 star S2 B1. Okay, because these two are equal, they are actually tau related. And if we continue this process, finally we arrive at an minus 1 star Sn minus 1 Bn minus 2. But this Sn minus 1 Bn minus 2, it's equal to, from this set of equations, it's equal to Tn minus 1 Bn minus 1. And now this An minus 1 tensor Tn minus 1 Bn minus 1, it is same as An minus 1 Tn minus 1 tensor Bn minus 1. So this is equal to An minus 1 Tn minus 1 tensor Bn minus 1. Now what's this An minus 1 Tn minus 1? We'll see this from those set of equations. You can see those set of equations here. Look at this, it's An minus 1 Tn minus 1 is Csn, so it's Csn, it is Csn, it is equal to Csn tensor Bn minus 1, and that's equal to C tensor Sn Bn minus 1, which is equal to C tensor D from these set of equations. So thus A tensor B is same as C tensor D. So that proves the one of this lemma, one part of the lemma. Now we prove its converse part actually. So conversely assume that A tensor B is equal to C tensor D in the set A tensor B over S. So that means they are actually tau related. AB is tau related to CD, but this relation tau is generated by, it's an equivalence relation. It's the equivalence relation generated by the relation T. So you have already done in chapter 1 in unit 1 that whenever we have a relation R E, which is an equivalence relation generated by the relation R, and if any two elements are related, are RE related, then we have a set of transitions from the first element to the last element. So that means we can find a sequence of transitions. Then we can find a sequence of transitions. A sequence of transitions like this, which starts with the pair AB. Say this AB is equal to, suppose the first element of this transition is P1 Q1, and this is the first transition, it goes to P2 Q2, it goes to P to Q2, and then this P to Q2 will go to P3 Q3, and if we continue this, finally we will get the last element, that's P and Qn, which is equal to the last element CD. So we have this sequence of transitions from A, B to C, D, where this transition means that what this transition means, that it means that this Pi Qi plus 1 Qi plus 1, it belongs to T, or it belongs to its inverse, or this belongs to T. It's P here, not A. It's P I plus 1 Q I plus 1 P I Q I belongs to T. So that either this pair belongs to T or this pair belongs to T inverse. In other words, pair belongs to T inverse means that this Pi plus 1 Qi plus 1 Pi Qi belongs to T. So but each transition is actually a move. So in T, what's T actually? But this T is actually this. T is actually this set. A is B, A S B. So this is our T actually. So if this pair belongs to T, that we can say this is the right move, because S moves from left to right. If its reverse belongs to T, that means if it belongs to T inverse, then we can say there is a right move from there's a move from right to left. So here it's left to right. S moves from left to right. So we have actually two types of moves, because at each stage the pair, at each transition the pair either belongs to T or it belongs to T inverse. Whenever it belongs to T, it means that we have a right move, and whenever it belongs to T inverse, that means there is a left move at that moment. So at each transition, at each transition the element of S, either moves right, either moves right. Right moves means that is we have move like this, ASB transition ASB. That means this transition, the pair belongs to actually T in that transition. Or left move, So left move means that ASB goes to ASB. So that's a left move. Now we see that if we have two successive right moves or two successive left moves, then we can club these two right moves into a single move. Two successive move right, two successive move right, two successive move right transitions, two successive move two successive right move right transitions, such as this ASB, it goes to ASB. Then we have another right move, that means this A times SB, it must be equal, it must be of this type, A dash S dash, A dash S dash, then this is SB, then there is again a right move, it's A dash S dash SB. So we have to can be combined into a single transition. This can be combined into a single transition, such as like this. Into a single transition we have this ASB. It's equal to, what's A is equal to A dash S dash S, A dash S dash B, and then there is a move like this, A dash S dash S B. So we have a single right move here. This A is equal to A dash S dash, okay? A is equal to A dash S dash. Then the final element of these two moves is this, and this is the initial element, this is the final element, and we have a single move. You can see single arrow. So similarly, any two successive move left can be combined, into a single left move. So it means that there is no success to right moves or to left moves. In other words, we can say these moves are in alternate. So if the sequence starts with left move, then the next move will be the right, and next move will be left, then right, then left, then right. So moves are alternate actually, left and right. There are no successive right moves or left moves, because we can club the two right moves into a single right move. So we may assume that. So we may assume that. So we may assume that move right and move left. Move right and move left. Move right and move left. Transition is alternate. Transition is alternate. We may also suppose that the sequence begins with the sequence of transition. We may also suppose that the sequence of transitions begins and ends. Begins and ends with a move right, with a move right. With a move right. Okay. So the first transition, which is AB, which is equal to P1 Q1 transition P2 Q2. We can assume that this transition is a right transition. Right transition means that this P1 Q1 is of this type. P1 Q1 is equal to, say, A1 S1. Then this is same as Q1, and then there is a right move. It means that this P2 Q2 is of this type. It's A1 S1 Q1. Q1 is here B. Okay, so I can write here it as B. So we can assume that this sequence of transition it begins with this move. right move, and also ends with right move. Suppose it's not, suppose it begins with the say left move. Suppose it begins with left move, then we can adjoin one more move which is the right move. Suppose this move is suppose this move is a left move. So left move means that this is this P1 Q1 is equal to P1 as it is, and we have a transition of this, it's here S1 B1, and then this P2 Q2 is equal to this S moves from right to left, it's a right move, it's a S1 B1. So in that case what we do, we add one more move. We take this element, we will make this as like this. Okay, let me write this as we'll write this as we adjoin one, actually one here. We'll take this as like this. We'll do like it's equal to A into 1 S1 B1. Then the move is like this. This one moves from left to right. Okay, it's A times 1 dot S1 B, just S1 B. So then this is it's like this. So we can add this move here. We will start our transitions with this move. Then this A S1 B1 goes to A S1 B1. Okay, then there is a left move. So we can always start the sequence with a right move, and also we can end it with a right move. If it's not true, then we can do the we can take these assumptions here. We can take we can take 1 here, A into 1, then we move this 1 from left to right, and then that means this move, this sequence of transitions will start with this move, which is a right move actually. Okay, so this assumption can be taken here. This assumption can be taken here. So what's now here? We have these sequence of transitions here, AB, which is equal to P1 Q1. Then there is a right move. P2 Q2. Then there is a left move. P3 Q3. Then again there is a right move, and ends with this. The last move is again the right move. This is the right move. Pn minus 1 Qn minus 1. Sorry, this is a left move, and this one is the last move now. This is Pn Qn, which is equal to CD. So this is the right move, this is left, and so on, and this one is the left move, Pn minus 1 Qn minus 1 to Pn minus 2 Qn minus 2 to Pn minus 1 Qn minus 1. This is the left move. Then finally we'll have a right move. So we have the sequence of transitions like this. Now let's take this first move here. So what's this first move? What it will give? This is this P1 Q1 to P2 Q2 is a right move. Since this P1 Q1 to P2 Q2 is a right move, so therefore this P1 Q1 it's equal to A1 S1, then P1 Q1 as it is. Q1 is actually B, and P2 Q2 it is obtained from this pair by moving this S1 from left to right. So this P2 must be equal to A1, and this Q2 it's equal to S1 B. So that the first move is the right move. Next move it's a left move. So this P2 Q2 it goes to P3 Q3 is a left move. So left move means that that S is with this Q2. We have a factorization from Q2 actually. Q2 and P2 as it is. What's P2? P2 is actually A1. So can take it as it's A1 here as it is. So if I will choose this Q2 has a factorization here. Q2 can be it's now it's a right move. Now it's a right, now it's a left move actually. Yeah. So this will come here, it's a1. So I will choose this. It's p2 q2, it's equal to, what's p2? P2, this is p2, p2 is a1 here, and here is a move from right to left, so q2 has a factorization like this. It's here t1, next I have b1 here, and then p3 q3 is equal to p3 q3, which is equal to, what will be p3? This t1 will go will join with a1. It will be a1 t1, and then here it's b1. So this transition gives this p2 q2, transition p3 q3, it will give this p2 q2 is of this form, p3 q3 is of this form. Now let's do one more transition. After this we have the next transition, which is p3 q3 to p4 q4. So we have this transition, p3 q3 to p4 q4. It's a right move, is a right move. So that means we have factorization for this p3. So p3 is of this type. What will be p3 here? So p3 has a factorization. So this p3 will be equal to say a2 s2, then q3. What's q3 in the previous transition? q3 as it is, but what's actual value of q3? That I have to see actually. What's q3? What's q3? q3 is b1 here. q3 is b1 here. So it's a b1, okay, b1, and then p4 q4, this s2 will move, so it will be s2 b1, s2 b1. Okay. So how we have these transitions. The next transition will be a left move, then p4 q4 to. So these total transitions are here odd because it begins with right and ends with right move, so that means total number of transitions will be odd. So I can assume this n is equal to 2n plus 1 actually, or you can say 2n minus 1. So what's the next transition? Next transition is this p4 q4 to p5 q5 is a left move. So left move means that p4 q4 it's p4 as it's, but what's p4? p4 is actually a2. It's as it is. So then q4 has a factorization, so it's s2 b1, and this should be here now t2. For left move we are taking the elements t, and for the right moves we are taking s. So you can see it here. First move, it's a right move. First move is a right move. So for the right move I have chosen the element s1, which moves from left to right. Then in the next move, it's a left move, I have chosen the element t1. T is actually which moves from right to left. So then in the next transition, what was the next? It was again the right move, so I have chosen the element s2. Then we have this transition. It is it's a left move, so I will choose t2 here. T2, then p2, and what's now this p5 q5? It's equal to p5. This it's a2 t2. A2 T2, then it should be here P2. This is a left move. So in general, what's happening actually in general what's happening? So at the odd stage, R2 even P3 Q3 to P4 Q4, it's a left right move. So I can choose the odd transition, the order transition, which is like this. So I have this P to I minus 1 Q to I minus 1 will go to P to I Q to I. In that case, this is a right move. This is a right move. So that means this P to I minus 1 Q to I minus 1. So for right move, we are choose the element. This element will remain the same, and you can see here what element this must be. P to I minus 1. You can see it here at for P3. But P3 is factorization, okay? And this Q3, it's equal to, it's actually here 2I minus 1. That I is here 2. That I is here 2. You can see if I will write this 3 as 2I minus 1, it means that I is here 2. So for I is 2, it's P3 Q3. This is equal to A2 S2. A2 S2. A2 S2. So it's I is 2 here, okay? I is 2. I is 2. So it is AISI. You can take this as AISI and BI minus 1. Okay? AISI. It's AISI BI minus 1. Then the next one is here P 2I Q 2I. This must be equal to this. It must be equal to AI, and this is SI BI minus 1. The next transition will be the right. It will be the left move. So this one P 2I Q 2I to P 2I plus 1 Q 2I plus 1 is a left move. Is a left move. And what's happening in left move? We can see it. We can see that what's that? What's left move? You can see this left move. P4 Q. What's P4? P4 is A2. It's 2I. That means I is here 2. P2I Q2I P2I plus 1. So I is here 2. So it's actually this 4 is equal to 2I. So that means I is 2. So I is 2. It's here AI TI BI. AI TI BI. It's AI TI BI. It's AI TI BI. Okay. It's a left move. That means P2I Q2I is equal to P2I Q2I is equal to AI TI BI, and then this P2I plus 1 Q2I plus 1, this will move from okay, it's not the right move, it's a left move. So again I want to see it here. What's this actually? This is a left move. So this TI is on this side actually. TI is on this side. So TI is on this side actually. So it's like this, TI BI, and then this will be here AI TI and BI. We can see this I can be varied from 2 to say m minus 1. Okay, you are taking here n. You can take n is equal to say 2m plus 1. Okay, because that n is odd, so you can choose n is equal to odd, and this is you can vary this I from 2 to m minus 1. So finally, what we have, what we obtain finally, finally I will take first the left move. So left move means that I have to choose the even here it will be here P2m to P2m minus. I will first choose the left move, then right move. So left means I have to choose A1 here, goes to P2m minus 1 Q2m minus 1, which is it's a left move. It's a left move, and in this left move it means that this P2m minus 2 Q2m minus 2, it's equivalent. It's a left move. So as here you can see, it's AI, it will be here AM minus 1, AM minus 1, then this is TIBI, this is T M minus 1 and B M minus 1, and that this transition P2M minus 1 Q2M minus 1, this is the left move, then right move is P2M minus 1, sorry, so this move must be the so last move is the right move. So right move means that first move is the right move, P1 to Q1, then left, then right. First move is the right move, last move is also the right move. So that should end with the odd number of transitions. There should be odd number of transitions here. So if I take this move P2m minus 1 Q2m minus 1 to P2m Q2m, okay, so n is here, you can choose n is here 2m, not 2m minus 1, just 2m. For these 2m we have actually odd transitions. Okay, so this the next this element must be equal to P2m minus 1 P2m minus 1 Q2m minus 1. This must be equal to, what's this, after applying the transition, this is AM minus 1 TM minus 1, AM minus 1 TM minus 1, then we have BM minus 1, and finally we have the last transition, that's this P2m minus 1 Q2m minus 1 will go to P2m Q2m. So these are the last transition, that's R2m minus 1 transition. Okay, P1 Q1 to P2 Q2 is the first transition, P2 Q2 to P3 Q3 is the second transition. So in that, so if we do this this will be the last transition, and it is the 2m minus 1 transition. In that transition we have P2m minus 1 Q2m minus 1 will go to P2m Q2m. So in that case what will be this, it's a right move. It's a right move means that we have factorization for this. So I have done this for the general transition, P2i minus 1 Q2i minus 1. It means that this is AISI, so it will be AMSM here. It will be AMSM. Sorry, it will be here AMSM. AMSM, then what should be here, again I have to see this m minus 1, it's m minus 1 here, m minus 1, it's B m minus 1. Then this P2m Q2m, it must be equal to AM SM and BM, and this is the last time, that's your CD. Now you can see from these set of transitions and the set of equations, we obtain those set of equations actually. So let's take what will be the value of A now. What's A actually? A is equal to, so I have to go back first. What's A actually? you can see here P1 Q1 is A1 B1, so P1 is actually A1 and P1 is actually A. This is your AB actually, okay? This is your AB, first element of this transition. So A is means P1, P1 is equal to A1 S1. It's equal to A1 S1. Then again you can see this what's this S1B, so that's Q2. What's Q2? Q2 you can see this this is Q2. Q2 is equal to S1B, but at the same time this Q2 is equal to T1B1, so that means S2B is equal to T1B1. S2B is equal to T1B1. S2B is equal to T1. It should be equal to actually S1. It should be S1B, not S2B. Let's go back again. So this should not be S2 here. This should be S1. So it's actually S1, not S2. Okay, it's actually S1 here. So it's S1 here. It's S1 here. S1B. Now next we will see this A1T1. We'll see this A1T1. What's A1T1 actually? And again you can go at that page. What's A1T1? What's A1T1? That's very important to see. That's very important to see A1T1. This is the transition and here we have P1 Q1, that's this P2 Q2. Okay, so let's see the next page here. So the transition is this is the first transition. Now I want to see A1T1. What's A1T1? A1T1 is here P3. You can see A1T1 is P3 here. And what's this P3? The other value of P3 is P3 is here A2S2. So that means A1T1 is A2S2. A1T1 is A2S2. A1T1 is A2S2. And similarly, you can see this S2B1 will be equal to T2B2. You can see this all. And finally, you can see this AM-1, AM-1, TM-1. I think you can see AM-1, TM-1. It's equal to at last stage, at last step, what's this AM-1, TM-1? Here is it here? This is the left move and this is the right move. I want to see the left move here. Left move previous. This is here AM-1, TM-1. So AM-1, TM-1 is actually equal to AM-1. Let's see the next move. This AM-1, TM-1, it's P2M-1, but here P2M-1 is P2M-1. You can see this P2M-1 is AM-SM. 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 Okay. AM-SM. It's AM-SM. That's equal to. What's AM? You can see this AM is actually equal to. This AM, sorry, this AM, what's this AM actually? AM is equal to C. So value of AM is C actually. Value of AM is C. So value of AM is C here. Value of AM is C. It's C SM. Okay, it's C SM. Then finally I have to see this SM BM-1. It must be equal to D, or you can can also verify SMBM minus 1 is equal to T. So these are the set of equations, and thus we have proved this lemma. Hence the lemma is proved completely. Hence the lemma is proved. Hence the lemma is proved completely. So this was the proof of this lemma. Now in the next theorem we will see this tensor product always exists in acts. Okay, that's the next theorem. And for this, to prove this theorem, we first show that this tensor is actually the set we have constructed A tensor B. It's actually a ST by system. It's actually a ST by system. That's the note here. A tensor B or S is ST by system. Is an ST by system. Not as an ST. It's TS by system. It's TS is a TS by system. Is a TS by system where action is defined by where action is defined by T times A tensor B is equal to TA tensor B, and A tensor B times S is equal to A tensor BS. And you can easily verify the action properties of it. Not TS, it's actually TU, sorry. It's actually TU. It's actually TU, sorry. It's TU. So this is for all T belongs to T and S belongs to U. This can be easily verified. So the next proposition is very important. That's the main theorem actually, in which we will show that the tensor product exists. Theorem. Let A be a TS by system. TS by system, and B and SU by system. SU by system, then this is the tensor product. A tensor B over S with tau natural is a tensor product, is a tensor product of A and B over S, of A and B over S. So first we need to show that there is a bimap from A cross B to A tensor B. Prove. This tau natural, it's obviously a bimap from A cross B to A tensor B over S, which is defined by where AB of AB of tau natural will go to this its tau class. So the image of AB under tau natural is actually the tau class of AB, and that has been denoted by A tensor B, and we will see that this map is a bimap. We show that tau natural is a bimap. We show that this tau natural is a bimap. We show that tau natural is a bimap. For the bimap, what's the definition of bimap? You have seen what's this bimap actually. So we have as comma b of tau natural, that should be equal to a comma sb of tau natural, but this is equal to as tensor b, and it is same as a tensor sb because they are tau related, and that's equal to a sb of tau natural. So that means tau natural is a bimap. This is a bimap. Next we will take any bimap. Let beta from A cross B to C be any bimap where the C is a TU by system. What's C? C is a TU by system. TU by system. We need to show that there exists a map from A tensor B over S to C. So define that map. Try to define that map. Define B tilde from A tensor B over S to C by, let's define this map by A tensor B of beta tilde, its image is equal to AB of beta, because this beta is a map from AB to C, so that means beta of AB must be an element of C. It's an element of C. So first we show that this map is well defined. This beta tilde is well defined. So let's take any two elements in A tensor B so that they are equal. Let A tensor B and C tensor D be any two elements in A tensor B over S such that they are equal. A tensor B is equal to C tensor D. Then by previous lemma, then by previous lemma, we have a set of equations. We have a set of equations of type star. Of type, तो हमारे पास स्टार टाइप की इक्वेशंस होगी, because we have seen that whenever this tensor is equal, then we have those set of equations of type star that we have proved in the previous lemma. Now we have to show that their images are equal. But the image of A tensor B is beta of AB, and image of C tensor D is beta of CD. So we need to show that beta of AB is equal to beta of CD. So we have AB beta. But what's A from this set of equations? It's A1 S1, A1 S1 B or beta, but beta is a bimap. It's A1 S1 B or beta. This A is equal to A1 S1. It is by star equations. And as beta, this is from as beta is bimap. As beta is a bimap, and that's equal to A1. What's S1 B1? It's T1 B1 by star, and again it's equal to A1 T1 B1 as beta is bimap. As beta is a bimap. This is here. This is beta actually. Yeah? Beta. Now this A1 T1, it's equal to A2 S2. It's equal to A2 S2 by those set of equations of B. Then there is beta. it's by star, by those set of equations. Now again apply the property that beta is a bimap, then this S2 will combine with B1, it's equal to A2 S2 B1 of beta, and continuing this you will see here it will be an minus 1 Sn minus 1 and Bn minus 2 of beta, but this Sn minus 1 Bn minus 2 it's equal to Tn minus 1 Bn minus 1 of beta by star, it is by star, and that's equal to An minus 1 Tn minus 1 then Bn minus 1, it's as beta is bimap, as beta is a bimap, and this An minus 1 Tn minus 1 is An, not a, yes, it's C, it's CSN, it's CSN, it's equal to CSN then Bn minus 1 of beta, it's by star, okay, and that's equal to C times Sn Bn minus 1 of beta is bimap, so this is C D of beta, so thus AB of beta is equal to C D of beta, so therefore beta tilde is well defined, beta tilde is a well defined map. And this diagram obviously commutes, you can easily verify this diagram commutes, we need to verify that this diagram commutes actually. This is C here, this is A tensor B over S, this is A cross B, and this is here tau natural, this is the beta tilde that you have seen, and this is the map beta, and you can easily verify that tau natural beta tilde is equal to beta. So that proves this hence this sphere A tensor B with tau natural is a tensor product, is a tensor product. That proves this theorem completely. Thank you.